Hello everyone, James from JTS Maths Tutoring here. Today we are going to be looking at an example of graphs and functions. So we have been given a function here and they want us to answer these questions based on that function. So the first question is determining the y-intercept. We all know that the y-intercept, this is where the graph cuts the y-axis, and at that point, x is equals to what? To 0. So we plug in x right here, and we can see at the end of the day that the y-intercept is equals to 0. All right, let's move on to the second question. Determine the horizontal and vertical asymptotes. So for detailed information in terms of how to determine horizontal and vertical asymptotes, we refer you to our Instagram page and our Facebook page. All right, but for this question here, we can see that this is an exponential function, which is like the basic form of an exponential function. So this is got a horizontal asymptote y is equals to 0, which is the x-axis. Right. For our vertical asymptotes here, we can set the denominator to 0 and then solve for x. So in our case here, the denominator is e to the power x. So e to the power x is equals to 0. It follows the fact that e to the power x can neither be negative nor 0. Hence, e to the power x is equals to 0 does not have a solution, for x is an element of what? Real numbers. Therefore, we conclude here that this function, if it does not have a vertical what? Asymptote. All right, we move on to the third question. So you use the sign pattern for the first derivative of x to determine the intervals over which f rises and where it falls, as well as the local extrema. So right here, you can see we will first start by getting the first derivative of f. Okay, cool, let's start. So this is like we are given two functions here, which is this, so f of x is like a product of two functions, x and then e to the power minus x. So we can actually solve this by the product rule, or I can rewrite this to have it in the form x over e to the power x, and I can make use of the quotient rule. But okay, I'm just going to use the product rule here. Okay, so we start by the derivative of x, which is 1. So we multiply 1 by e to the power x. Here we are, we have our e to the power x here, plus we get to the derivative of the second function. The reason why you don't see the plus sign here is because already the derivative of this is going to be a minus. So a plus and a minus is going to give us a minus at the end of the day. So you've got your minus here, right? So we have minus e to the power minus x, then multiplied by x. So this is where we are here. If we factor out our e to the power minus x, we are going to be right here, which I decided to write it as a rational function here. So if this goes down, it changes sign, so it becomes e to the power x. Okay, that is our first derivative. So whilst we are still there, let's just straight away go to d, which is the second derivative, before we answer where f rises and where it falls. Right. Okay, so I've taken this function here in this form now as a rational function, because this time around I want to make use of the quotient rule. So here we are, the quotient rule. So we first get the derivative of the numerator, we multiply it by the denominator, then we subtract the derivative of the denominator, we multiply it by that, all that over the denominator squared. Okay, cool. So all right, so here I'll get minus 1. So minus 1 multiplied by e to the power x. This is where you are getting the minus e to the power x here. Minus, what is the derivative of this function here? The derivative of e to the power x is e to the power x. So it's minus e to the power x multiplied by this function here, which is 1 minus x. So now if I distribute this inside here, I'm going to get minus e to the power x plus x, e to the power x, which is, after simplifying that, this is what you get, minus 2 e to the power x plus x, e to the power x. If I factor out, that is here where we are. So you can see that I've got e to the power x here, and I've got e to the power x squared right here. So these two, they cancel each other, and this is the final result for the second derivative of f. All right, let's go back to C. The intervals over which f rises and where it falls. Right, so they said make use of the sign what? Of the sign pattern. Right, so I'm coming back here to my first derivative here. I need to get what are called what critical points. So what are critical points? These are simply points where the function is actually defined and its derivative is 0, or it is what? Undefined. And I'm looking at this function here. I can see here that the only critical point which I'm going to have here is 1, because if I plug in 1 here, I'm going to get 1 minus 1, which is 0. So 0 over 1 is going to give me 0. Okay, cool. Because remember, from what we deduced right here in B is that e to the power x can neither be negative nor 0. So it's always going to be what? It's always going to be positive. All right. So the critical point for f for the first derivative is 1. And this critical point, it actually splits the number line into two distinct intervals. What are these two distinct intervals? It's all the numbers which are less than 1, which are on the left of 1, and all the numbers which are greater than what? 1. So this is what we are talking about here. So assuming that this first derivative had to say two critical points, those two critical points, we're actually going to split the number line into what? 3 distinct what? Intervals. All right, cool. So here we are. How do we arrive at this here? So here I'm simply going to plug in any number that is within this interval, any number that falls within this interval here. All right, for instance here, let me plug in 0. So I'm saying 1 minus 0, what I will get there is 1, which is what? Positive. So plugging in that into this function, I'm still going to get what? Right, that's going to be 1 there, 1 minus 0, 1, this 1 over 1, which is still positive. This is why we have got a positive here. All right, then if I am to come to this interval here, let me choose any number as long as it falls within this interval. So for instance, let me get 2 here. So 1 minus 2, you get minus 1, which is a negative number. Right, so let's plug in that very same number into, so okay, 1 minus 2, that is minus 1, and I've got this e to the power 2. Okay, the final result is still going to be a negative number. All right, so I've got some notes here to help you understand how to manipulate this sign pattern. So say f rises where there are positive signs on the sign table, and f falls where there are negative signs on the what? On the sign table, right? And there is going to be a local extrema, which is either going to be a minimum or a maximum, where the first derivative changes what? Sign. So we are looking at this sign table here. All right, cool. So there's going to be a local maximum when the first derivative changes from positive to negative, and there's going to be a local minimum when the first derivative changes from negative to positive. Okay, so let us answer these questions. We can see here that f rises within this interval because this is where it is positive, and f falls within this interval here because this is where it is what? Negative. So there we are. That's the answer to that question. So there is actually going to be a local minimum at, because where does it change? You can see from this sign table, it changes here at 1 from positive to negative. So what we do now is that we plug in this 1, not into this first derivative, but into the original what? Into the original function. So we can see that there's a local maximum when x is 1 and y is 1 over e. All right, let's move on to the next question, which is your D. So use the sign pattern to determine where the graph of f is concave up and where it is concave what? Down, and also check here whether we have an inflection point, that is if we have one. All right, so this is the reason why we decided to look at this before we go to D. All right, look at this. If we go down here, right, and we are also making use of a sign pattern, right? So we can see from there, from the top part, for the first derivative, that we've got x minus 2 over e to the power x. All right, so this is what we are going to have here. All right. The reason why we are not going to have e to the power x here, or why we didn't even bother here, because it's always going to be positive. So it doesn't really going to change whatever is going to happen at the end of the day there. All right, cool. So we have it here, and we've got our 2 here because that is our critical point when it comes to the second derivative. And that's this critical point is splitting the number line again into 2 distinct intervals, which is all the numbers on the left side of 2, which are less than 2, and all the numbers on the right side of 2, which are all numbers greater than what? 2. So we do the very same thing. So you notice that when we plug in any number based on this interval, just like what we did here, we'll get negative here. The final outcome is going to be negative there. We get a positive number there and a positive number here. So I'll leave it up to you to plug in any number. Right. So I also gave you some notes here to actually help you understand where this thing is coming from as far as your sign table is concerned. So F is actually concave up where there are positive signs on the sign table. F is concave down where there are negative signs on the sign table. And what is an inflection point? It is simply a point on a graph at which the second derivative changes what sign. Basically, we are looking at where concave what changes here, direction, whether is it concave up or concave what down. So to answer that question, F is concave up on this interval because this is where it is positive, and it is concave down on this interval here because this is where it is what negative. And we can see here that at 2, we have concavity changing there from concave down to concave up. So we plug in these 2, not into the second derivative. Take note of that. I've seen many students making that mistake. You plug it into the original function. So when you do so, you'll notice that we have got a point of inflection when x is equals to 2 and when y is equals to 1 over e to the power 2. Right there, this is where we are. We've actually answered that question. So in our next example, again, of graphs and functions, especially when it comes to vertical and horizontal asymptotes, we are going to do this very same question, but making use of limits. Thank you so much for tuning in. If you have any questions, please post them on our Facebook page as well as our Instagram page. Allow me to do